Okay, hi everyone. Welcome back to lecture 5. And today we're going to be talking about hashing. Okay, so the outline of the lecture today will be, I'm going to introduce you to hash functions. And again, I'm going to, we're going to go through the question of why hashing and what is hashing, right? So I blended the two questions, right? Like why is hashing? And we're going to see like what it is and what's this purpose. And it has actually many purposes beyond the ones that I'm going to talk about here. Okay. And then we're going to start discussing how to hash. And then in the second part of the lecture, we're going to talk about how to construct hash functions, which are actually efficient to compute, right? As you're going to see. Okay. So, all right. All right, so before we begin talking even about hashing, we need to talk about computational models, okay? So before we talk about hash functions, right, our model of computation here is important. And in this lecture, and usually when I'm talking about hashing, and if not in the homework, I will tell you like, oh, here is we're in the bit model, right? Like the Turing machine model that you guys know. But for today, we're gonna talk about the word RAM model, right? So what is the word RAM model? So in the word RAM model, all elements that you're going to deal with, okay, they're integers that fit in a machine word of W bits. Okay, so like if you think about it, like what the word RAM model is that all the elements that you have, they're just integers between like 0 to like 2 to the W minus 1. Okay, so that's essentially what the elements are. Or if you wanted to add like negative numbers, you can do, like minus 2W minus 1 to like all the way to 2W minus 1 minus 1, right? So you have all those like ranges, okay? But these are all the integers that will fit in a machine word of W bits. And the basic operations here, like if I take two integers and I want to compare them, or if I want to do arithmetic with them, like multiply, add, right, subtract, divide, like, and even bitwise operations on these, on each word, okay, it will take theta 1 of time, okay? That's just the assumption that we have. And we can also access any position in the array, right? So we think of our like memory, okay, in the word RAM model, our memory is this array, right? So we have an array of like 2 to the W elements, right? So we have like this array. So the word RAM model, our memory is an array. And we can access any position in the array in theta of 1 time, right? So the accessing like doesn't take too long, okay? So this is the model. Is that clear so far for everybody? Okay, and now you may ask, you may stop and ask, well, wait, but aren't we working on like asymptotic analysis of algorithms? I mean, aren't things going to infinity, right? So why do we have this word RAM model that things don't go to infinity because they're all the elements, like they're integers that fit in a machine word of W bits, right? So the integers are certainly bounded and there's nothing going to infinity. So the thing is, this model is still relevant for problems of good enough size. So, and what do I mean by good enough size? I mean, good enough size that, so the asymptotics can actually kick in, right? But these numbers are not super huge that they don't fit in the machine word, right? So you think like we're usually dealing with problems where we have enough memory to deal with the problem. Whenever you use the word RAM model, like you're dealing with problems that are large enough that asymptotics can kick in, right? Because usually when we say like n going to infinity, all we mean is like there is a certain constant such that if your problem size is bigger than that constant, like everything works, right? So that's what asymptotic analysis is. But here, there's the happy medium that like whenever our asymptotics start to kick in, and then there's a bound at which we have enough memory to deal with, right? Like this is where kind of this word RAM model becomes very relevant, right? Because then we have asymptotic analysis. We can use both asymptotic analysis and this model, okay? But otherwise, if you don't want to use the word RAM model and you want to use like the bit model, all you'll have to do at some point is replacing this theta 1 time per operations or whatever by, log n, where n is the size of your, like the integer that you're dealing with, okay? So, or log n times log n or whatever, like whatever cost of operations you're assuming, okay? So this is just a simplification to kind of abstract away the complexity of these operations, okay? So far so good? All right, so excellent. Now, okay, so what is hashing, right? So in hashing, we want to store O of n elements, which you can think of as keys, from a huge set, a set U, okay, U for universe, right? And here, let's say that assume that U is a really big set, okay? But we also assume that the number of elements in this huge set is smaller than our total memory, okay? So in particular, like log n is less than W, which means that like every element of this universe fits in exactly one word. Does that make sense? So, and that's the sweet spot, right? Like it's a huge set, but each element of the set would fit in a word. And here we're imagining that M, right, which is the size of the universe, is much bigger than N, like the number, which is roughly the order of the elements that we want to insert, right? That we want to in our data structure, okay? And this data structure that we want, right, it should support insertions, deletions, and search as efficiently as possible. Right? So, I mean, you guys are all familiar with it, right? Like in dictionaries, for example. All right. So, all right, let's see like a naive approach, right? So a naive approach is let's just use an array A of M elements. And initially, right, AI is equal to 0 for all I between 0 and -1. And when a key is inserted, when you say, oh, insert a key, right? We set the entry, the ith entry of A to be 1, right? We do have enough memory for this, and we can certainly do that. Now, what is the analysis of this data structure? Well, insertion takes constant time because I'm just flipping a bit, right? Just flipping a bit from 0 to 1. Deletion takes O of 1 time because I'm just flipping a bit from 1 to 0. And remember, in the word RAM model, I can access any position of my memory in constant time, right? So this takes constant time. And to search also takes constant time because what happens is that to search if an element I is there, I just need to look at the entry of the array A of I. Does that make sense? So all of these take O of 1. So while you may think that this is wonderful, right? So this part is really wonderful, but the memory is actually pretty bad, right? Because we're storing like O of M memory, right? Our array has size M. And remember, M is much bigger. We're only going to store N elements, and N is much, much smaller, right, than M. Okay. So we're using a lot of memory to achieve this performance. And certainly we don't like to like just allocate all this memory, which is unnecessary, right? So the question here is, okay, this is not as efficient as possible because the memory is pretty bad. So, okay, so we also want to achieve some optimal memory O of N, right? Or as close as possible to O of N that we would like to have, right? And for this, we're going to use this technique called hashing, right? So what is hashing? Okay, hashing consists of a hash function, which is just a function from the universe to the set like 0 up to n-1. So we're just going to assume that the memory is actually n, and we want to store O of n elements, right? So we're going to use something of memory n. So let's say, suppose that you had like n over 2 elements or n over 4 elements, right? You're going to try to create a table of size n for those n over 4 elements, right? So, so the hashing is composed with a hash function, right? Which is a function from the universe to the set 0 up to n-1. And the hash table is the data structure that consists of a table with n cells, right? And the cells are indexed by 0 up to n-1. And each cell stores a word, right? So we have a table and a hash function. Okay, so a hash table is a table, which is your data structure where you're going to store stuff, and the function that will tell you, oh, this key will be stored in this entry of the table. Does that make sense? Okay, great. So, okay, and from now on, we're just going to define memory as the number of cells, right? The number of cells of your table. or the auxiliary cells, like the table may use like auxiliary, as we're going to see later. Okay, so, all right. So, or actually, sorry, we're going to define the memory here just as number of cells. Okay, so just it is as is here. All right, now you may ask, why is hashing useful? Okay, of course you all use dictionaries, so you kind of know why it's useful, but there's even more reasons for why hashing is useful, right? So designing efficient data structures like dictionaries for searching, like you all know that and probably use that a lot, is also used in data streaming algorithms, as we're going to see later, is also used to removing randomness from algorithms. Okay, sometimes we would like to remove randomness from algorithms, and it's very useful there. It's highly used in cryptography, and it's used in many other areas of complexity theory and in many other types of data structures as well. Okay, so, all right. So, okay, now let's talk about the challenges in hashing, right? So here, the setup is the following, right? So we have a universe U of size m, much bigger than n, right? And n is the size of the range of our hash function, right? And let's say that we have some O of n elements of U in the hash table. All right, so this is our setup that we just discussed. And now, ideally, we would want a hash function, right, that map different keys into different locations, right? Because if we had a hash function that mapped different keys to different locations, what would happen? What happens is that we're pretty much in the same setup as the big array that we talked about before, but now with a much smaller array. Does that make sense? So instead of having that array A that we had before, we would construct a much smaller version of it that had the same characteristics, right? So we're saving on the memory. Okay? So, all right. And for that, we need to define what is the bad event, right? So the bad event here is what we're going to call a collision, right? So we say that a collision happens for a hash function h with inputs x, y in the universe if x is different from y in the universe, but the hash function mapped them to the same entry, right? So what is this collision? So let me just, the collision in words, right? In picture is what? I have my elements of the universe U, let's say X and Y. And then here I have my hash table. Let's say that I have this entry here. And now I'm mapping X and Y via the hash function to the same entry, right? So this is what a collision is. So this is the bad event. This is what we want to avoid, right? In the perfect world, like, you know, we would have X and Y going to different places, right? But you notice that if we pick any hash function, right? It's impossible to achieve no collisions for any set of size, let's say n over 2 or something, right? Without knowing the keys in advance, right? And why is that? Because any function from U to 0 up to n minus 1 will have a collision by the pigeonhole principle, right? Just because the set U has more than n elements. So, you know, there will be 2 elements that will go to the same entry, right? So if we don't know the set in advance, it could be that the set has these 2 entries like X and Y, like these 2 keys, X and Y, right? So kind of without knowing the set, the keys in advance, it's impossible to achieve no collisions, right? And the thing is, as we're going to see later in today's lecture, there's the problem of perfect hashing, which is even when you know all the keys in advance, is still not easy. It's possible, it's possible, and we're going to do it today, but it's still not easy to construct a hash table for the keys, even if you know them in advance. But we're going to see how to do it. Okay, so all right, something to look forward to. All right. So, all right. So what are we going to settle for? So since we cannot have, we cannot achieve like no collisions without knowing the keys in advance, what we're going to settle for, right? All we know is that, let's say n over 2 elements are going to be inserted. So what we're going to settle for is that we want the number of collisions to be small with high probability. Does that make sense? Because what happens, like, if you remember our example of the big array, there's never any collision at all, right? By the construction of the array. But now, suppose that we had an array of half of the size, and each array stores, like, let's say the first entry of the array stores the element either 0 or like n+1 or m over 2 plus 1, right? And then you just pair them up. Maybe let's say like the first entry stores the elements like 0, 1, the second element like 1 and 2. So you're storing 2 bits per entry. It's still constant time because every time that I need to check if an element is in the array, I just go to the entry, and then there's 2 entries that I need to check, right? One for, let's say, 0, one for the element 1, right? So if I had, let's say, like if at most 2 elements were assigned to the same cell, I still have search time, deletion time, and all of that in O of 1, right? So long as I know that each cell has constant load. Does that make sense? So collisions are not bad. The only bad thing is many collisions, right? That's bad. So we would like to avoid that. Okay. All right. Okay, great. Does that make sense here? And here is also where you start seeing like one of the benefits of probability, right? Because we don't know the set, like there's nothing we can do about it, right? The only thing that we can do here is like, oh, I'm going to come up with a random assignment. Like I'm going to create a random function. And this function, I'm hoping that with high probability will be good for the set that's coming to me, right? So in this sense, like randomness here is kind of essential for you to like achieve a good result without knowing what the input is like, right? So this is another use of randomness that, you know, you should keep in mind, right? Is that randomness is good whenever you don't know what is coming at you, right? All right. Okay, so here's our solution, right? So since our like we cannot construct one hash function for a hash table, right? Our hash table will have size n, but we need a function for it, for the hash table. So what we're going to do is we're going to construct a family of hash functions h, right? Such that the number of collisions is small with high probability. And when we pick a hash function uniformly at random from this family. So we're going to construct a family of functions and say, okay, I'm going to pick a random function from this family. And this function would be good with high probability, right? So what do I mean by that? Mathematically speaking, like the simplest version to keep in mind, and we're going to look at it very formally later, okay, in the second part of the lecture, is the following. What we want, right, is the probability. And now let me explain what this is, right? So this is the probability. So the probability when picking h uniformly at random from h, right? When I pick this hash function, and what we want is for all x different from y in U, what we want is if you pick any 2 elements, like any 2 keys in the universe, right? What we want to say is that if I have these 2 keys, like let's think that these 2 keys are fixed, right? But it should work for any pair. If you pick any pair of keys, right? So any pair of keys, what we know is that the probability when picking h uniformly at random from this family, the probability that there is a collision, right? So this is, they collide, is less than or equal than 1 over poly n. Okay, does that make sense? So this is what we're striving to. Okay, so, and we're going to see how to achieve that in the second part of the lecture, right? We're going to see even how to achieve it now, but you'll see that there will be problems that we need to fix. Okay, is this so far so good? Just this outline, the goal? Okay, so now here's the assumptions that we're going to make, right? So the keys are independent from the hash function we choose, right? Because they don't depend on the hash function. We just have a family, and the keys are the keys from the universe. And also the assumption in the first part of the lecture, all the way until the end, okay, will be that we do not know the keys in advance, right? So, but only in the end, we're going to say, oh, even if we know, now how do we solve this, right? So, all right. So here's a harder problem. We're going to start a harder problem first. Okay. So the question is, we still could have collisions, right? So how do we handle these collisions if we have the collisions? So there's many ways of handling it, right? But we're gonna see just one for today, or we're gonna see two today. But
so the probability is based on the hash functions, not on the x and y, right? So x and
exactly.
y is, okay.
Exactly. Yeah, it's for any pair. Like if you take any two keys, the probability has to be small. Exactly. Okay, great. So all right. So let's just do the first approach, right? Like so here's the thing. Let's take from all the functions from the universe U to the set 0 up to n-1, let's just pick one function uniformly at random. Does that make sense? And here, sorry, I think, because of the homework I did, the interval 0, 1, here, this interval 0, n-1 is, I'm just using this for shorthand for 0, 1, 2, all the way up to n-1. Okay, so it's different than that, the usual interval that you've seen in calculus or analysis, okay? Just a shorthand to not write this big thing. All right, so from all these functions, let's just pick one uniformly at random, right? So, all right, and if you notice, choosing a function h uniformly at random is exactly the same as our balls and bin setting, right? And why? Because to pick a completely random function from u to 0 up to n-1, all we need is to say what? Well, the u is the set of balls, and 0 up to n-1 is the set of bins. And your function is just deciding for ball k, where does the ball k go, right? It will go to the bin h of k. Does that make sense? So this is exactly the same setting as the balls and bin setting. If we pick the function h to be completely random, right? Does that make sense? All right. So now, so then what happens here is that if we store, so let's say that we actually store n keys, right? Like, what is the expected number of keys in any location, in any cell? The expected number of keys is 1, right? Because I have a table of size n, and let's say that I have n elements. Does that make sense? Right? Because this was just the thing, like if I threw balls independently at bins, what is the expected number of balls in the bin? Right? That's exactly the same question. So the expectation that we saw there was 1. But also, what did we see? We saw that the maximum number of collisions, like the maximum load of a bin, right, was O of log n over log n, correct? So this is the maximum load in a cell, right? So what we expect, what is the typical, and this is actually typical, right? So this was the typical behavior that we saw. So what we know is that, okay, so I know that with high probability, there will be one cell that actually will have to store log n over log n keys, right? So, okay, so now how do we resolve this? Because there will be one cell that has this many elements that are mapping to the same cell, right? So what we do is, well, the way to solve collisions is instead of having one element per cell, we just have each cell to be like to point to a linked list, right? Just have each cell point to a linked list. And what do? Well, to solve the collisions, all the keys hashed into a location I, we store them by a linked list. So my cell will point to the entry, like the first element of the linked list, and then we just keep going, right? Like in the doubly, let's use a doubly linked list, right? So then this is known as the chain hashing, okay? So this way of solving collisions is known as chain hashing, okay? And you can see that, okay, in this case, what is the running time of all of our operations? So with high probability, the maximum load is O of log n over log n. So, so here we have like insert can still be done like in O of 1, right? But then, search like will be done in O of log n log n, right, with high probability, because to search, I need to go to the cell that I'm mapping. And once I go to the cell, I need to search through the doubly linked list, right? So then that takes the length of the doubly linked list. And also to delete, right? Deletion also takes O of log n log n, because with high probability, right? So this is the high probability, because here what happens to delete, I need to search, right? Does that make sense? So, okay, so it's not bad, right? Because log n is usually not a huge number, but can we do better, right? And still we're going to see that there's other problems. Right. And now the thing is, you could say, well, Rafael, we also learned in the last lecture, right? Like the power of two choices, that it decreases the load from like log n over log n to log n. So why, instead of just picking one random hash function, let's pick two random hash functions. And then we always assign it to the cell that has the least number of elements, right? Just like we did in power of two choices. This reduces the load, right, to O of like log n, right? So now here, and then and we can do that. So let's suppose that we did that. So our running time is like O of log n, which is kind of wonderful, right? We can just use that and it'd be great, right? But okay, but we haven't seen where the problem is yet, right? Yeah.
Yeah, I have a question. So if I remember, in the balls and bends setting, we assume that that the probability of choosing each bin is 1 over n. So the hash function should have like a criteria. The hash function should equally distribute, like the probability that you're going to get n-1 is the same the probability you get 0.
Right. So, and let's just, yeah, we're assuming here that we have perfect randomness, right? So you can generate this the uniform distribution quite easily, right? So we're
so the hash functions basically should be like, it should be the same for each bin. Like 0 should have the same amount of possible elements in U, like 1, like 2, and n-1. Right?
Okay. That's a great question. And I think you're getting ahead. You're getting to the next slide. So let me go to the slide and I think I'll answer your question then.
Okay.
Yeah? Because you're right. Now, Hazem's question, if I may just rephrase it, is like, okay, Prof, how do we actually construct the random function? Right? Like we need to I still haven't shown you how to construct it. All I said is that it's analogous to the balls and bins, right? But how do I construct a random function that has the same behavior, right? So, okay, before I go, Nafisa, do you have your question, or you unmuted? But
yeah, I probably it's a very stupid question. So I'm just curious. You know, we are always talking about taking probability and what is the maximum number of collision that can happen. But since we are not actually considering what kind of like numbers that we are gonna get, so it can actually happen that one bin will have all the number.
Right.
The worst case.
Right. Worst case, but remember, we don't want worst case. We want with high probability, right? Like the probability. By the way, first answer that I need to give you is that there's no stupid question. The only stupid thing is to not ask a question when you have it, right? So that's a great question, right? And why is that? Because it just that's why we are emphasizing, right? Like the fact that like here, we're not interested in the we're not interested in the worst case without any randomness, right? We use randomness to say with very high probability that worst case will never happen.
I see. And
right.
I have another question that probably what Hazem also asked, I'm not so sure, that like the hash function we are choosing, why is it analogous to a bin? Like I can use a like very naive hash function that can have a very worse result.
Right. I mean, you can use any function, but this is just the first approach that we're thinking. This is all that we're thinking. This is just the first thing that would come to your mind is like, oh, let's just pick a perfectly random function. I mean, why not?
Okay. I got it now.
Yeah.
Okay.
Yeah.
Thanks, Professor.
No problem. All right, great. Any more questions before we go on? And I'll get to Hazem's question right now. So I think, all right. So, all right. So random, like what we saw here is like random hash functions look very good. All we need is like 2 perfectly random hash functions and we're great, right? But the thing is, we have not discussed the following, right? So how much resource does it actually take to compute a random hash function? Right? We didn't talk about the time it takes to compute a random hash function. So let's take a look at that. And for that, I need to describe how we're going to create a perfectly random hash function, right? Like we talked about. So here's the thing. So to store the entire function h, okay? So where's the complexity? Look at where the complexity of a truly random function is, because to store an entire like function h, like it requires O of m cells. And why is that? Is because a truly random function, I have to say to you like, okay, key k will go to entry, let's say 0. Key k2 goes to entry 1. I have to tell you exactly which k, right? And how do I construct this random function? I would just say, you know, if I want to construct a truly random function, for each k, like for each key, like key 0, pick a random value between 0 and n minus 1, uniformly at random. And then you assign that value. Once you assign that value, it's done, right? Like now you go to the value 1. Does that make sense? So, you know, let's say that, you know, suppose that m here was maybe like 10,000 and n is equal to 10, for example, right? Like if I wanted to create a truly random hash function, I just need to say, well, for element, you know, 0, I have to assign some value. Let's say I'll assign the value 5. And then element 1, I'm going to assign the value 3. Element 2, I'm going to assign the value 10. Element 3, I'm going to assign the value 5. Does that make sense? I'm picking, but every time a new number comes, I have to pick a uniformly random value from 0 to 9. Does that make sense? Sorry, and this is 0 to 9, so we should have 9 here. Okay, so that's how I construct my random hash function. Does that make sense? But now, because my function is truly random, every time a new key comes, I have to pick a new value. So to store my entire function, I have to store this map for every entry, for every key. Does that make sense? Great. And now, like, okay, so now here's the thing. But then you might say, but Prof, like, you know, we're not going to see all the elements, right? So, but even if we only like, but then now suppose that, you know, we're only storing like 5, or let's say 4 elements. You may say like, Prof, we may just say, you know, we're only going to see 4 elements. So why not only store the elements that we saw? Right? So even if we stored only the elements we saw, okay, it would require us O of n time to even evaluate h of x. Does that make sense? Because to evaluate h of x, I first need to know if I already pre-computed my value of x, right? For example, suppose that m is 10,000 and my numbers are 0, 1, 2, 3. Right? So whenever I receive 3, I need to figure out, oh, have I actually computed h of 3 before? So then I have to go through the list of my elements, and I have n of them, and I have to, oh, is 3 in my list? If 3 is in my list, then I know the value of my function. If 3 is not in the list, I have to pick a uniformly random like cell to store it. Does that make sense? Yeah. So that's why like the random hash function is not great, because random hash functions are hard to compute, right? They're really hard to deal with. So the question is, okay, so for random function, so and then by exploring this, where the complexity lies, right? So actually for random function, right, what I told you in the previous slide is a lie. I was lying to you, because for the random function, all the operations like insert, delete, and search, they actually take O of n time. Right? And why is that? Because the complexity of computing, of evaluating the random function is O of n. Right? So even deciding which cell to look at will take me O of n time. Does that make sense? the O of 1 that we assumed was kind of a wrong assumption because we were saying, oh, you know, it's easy to compute the random function. It's not. Does that make sense? Okay, great. So then the question is, how do we cope with this computational problem that arose with randomness, right? Like randomness, we saw that it's great. It looks great, but when you look at it computationally, it's really bad because the complexity was kind of whatever we did before was wrong. Because once we look at how easy it is to compute a random function, we had a problem, right? So how do we cope with this computational problem?
I'm sorry, like going back, but I'm still confused with the balls and bins. So just one thing, in the balls and bins, each ball was different, right? And it was the same, right? The different was the random variable that you chose to which bin it would put, right? But
no, each ball was different. Each ball was different. Right. I just had, and I mean, the balls, like the balls are identical in the sense that I'm going to take my first ball and throw it somewhere. And then I take my second ball and throw it somewhere, right? I throw them the same way. Right.
So with the hash function, the value of the element in U actually makes it like the value of H depends on the value X, right? On the X element of U.
So correct, but it's the same because think of the balls are all different in the balls and bins. You have M balls, and right. Each ball you're gonna throw in a bin. Let's say throw ball 1 in a random bin. Suppose the ball 1 fell on bin 7. If you look again, you say, okay, where did I throw ball 1? Oh, it's in bin 7. It stays there, right? So you can say that like bin 7 is the value of the function of ball 1. Does that make sense?
Yes. Okay, so when you calculate the expectation of the hash function, you choose a hash function at random, and you right. you threw all n balls, right? Yes. And then you found that the expectation is 1, and the thing is of log of n divided by log n, right?
Right, because I threw n balls. I don't know which balls they were, right? But I threw n of them. I threw n distinct balls.
And when because the hash function is random, it's analogous to the random variable.
Exactly, it's analogous to the balls and bins where I had n balls and n bins, right?
Right. Okay.
So it's exactly the same, right? It's just like from all the universe of all balls, if you pick any n different balls and you throw them into bins, you have exactly the same thing as we did in the last lecture right. For n balls and n bins.
Okay. Okay. Yes. Okay.
That makes sense?
Yes.
Perfect. All right, so now we got to the point where we need to deal with this computational problem that arose with randomness, right? And we're going to see that in the second part of the lecture.